Chairman, and good afternoon, everyone. I'm Saya Ajito from Tohoku University, Japan. Today, I would like to talk to you about our recent research, hydrogen diffusion behavior in tempered martensitic steel, effect of static loading. As you know, hydrogen embrittlement occurs under loading condition. So in order to investigate the effect of hydrogen embrittlement mechanism, it is important to clarify the effect of stress on hydrogen diffusion behavior. Previously, hydrogen permeation tests were conducted under loading condition. For example, Rappert et al. Reported the relationship between the diffusion coefficient and stress as shown here in tempered martensitic steel. In the region of elasticity and microplasticity region, the hydrogen diffusivity is constant. On the other hand, hydrogen diffusivity decreases in generalized plasticity region. Therefore, it has long been believed that stress has no effect on hydrogen diffusivity and plastic strain decreases hydrogen diffusivity. However, in martensitic steel has low elastic limit. It means plastic deformation occurs below yield stress. It is called micro yielding. In that case, there are two possible interpretations can be made for the constant diffusivity under elastic loading. The first interpretation is that both microplastic strain and stress has no effect on diffusivity, so diffuse hydrogen diffusivity is constant under elastic loading. Another interpretation is that microplastic strain may decrease hydrogen diffusivity as general plastic strain does, and stress may increase hydrogen diffusivity, and these effects cancel, and hydrogen diffusivity under elastic loading is constant. In order to clarify the real effect of stress on hydrogen diffusivity, it is required to consider or remove the effect of microplastic strain on hydrogen diffusivity. Therefore, in this study, we investigate the hydrogen diffusion behavior in tempered martensitic steel under loading and effects of microplasticity and elasticity on hydrogen diffusion behavior was investigated. Here is the experimental procedure. The material used in this study was chromium molybdenum steel. The specimen was annealed at 900 degrees Celsius, followed by oil cleansing to obtain martensitic steel structure. Then it was tempered at 400 degrees Celsius, followed by air cooling. Here is the engineering stress strain curve of the specimen. The yield stress was about 1400 megapascal, and tensile stress was about 1500 megapascal. Here is the experimental procedure of hydrogen permeation test. This is a schematic diagram used in this study. For the hydrogen detection side, the working electrode was specimen with nickel plating. Reference electrode was mercury oxide electrode. Counter electrode was platinum wire. The cell was filled with 1 molar sodium hydroxide aqueous solution, and specimen was polarized at 0.1 volt versus reference electrode. For hydrogen entry side, the working electrode was specimen. The reference and counter electrodes were same as hydrogen detection side. The cell was filled with 0.1 molar sodium hydroxide aqueous solution. The specimen was polarized at -1.2 volt for hydrogen charging. The duration of this hydrogen permeation test was 1 cycle per day with 16-hour hydrogen charging and 8-hour hydrogen uncharging. The hydrogen permeation test was repeated several times with various stress and strain conditions. Firstly, I would like to explain the result of the effect of microplasticity on hydrogen diffusion behavior. In order to investigate the effect of microplasticity on hydrogen diffusion behavior, firstly, we introduced microplastic strain in the steel by applying preloading of 500 and 1000 megapascal. The introduced plastic strain was 0.05% at 500 megapascal and 0.07% at 1000 megapascal. Then hydrogen permeation tests were conducted with various microplastic strain and without stress. Here is a transient of hydrogen permeation current. From the left graph, microplasticity did not affect on steady-state hydrogen permeation current. On the other hand, right graph shows the enlarged one with the initial half hour. You can see that the larger the microplasticity, the later the hydrogen permeation increase. Based on the hydrogen permeation current measurement, we calculated the hydrogen diffusion diffusivity and relationship between hydrogen diffusivity and plastic strain are shown here. Hydrogen diffusivity decreased with increasing microplastic strain. It means that microplasticity affected hydrogen diffusion behavior. So far, we investigated the effect of microplasticity on hydrogen diffusion behavior, and we found that microplasticity affected hydrogen diffusion behavior. It decreased hydrogen diffusivity. This result indicates that in order to investigate the effect of stress on hydrogen diffusion behavior, it is required to consider or remove the effect of microplastic strain. So we try to investigate the effect of elasticity on hydrogen diffusion behavior with consideration of microplasticity. In order to investigate the effect of elasticity on hydrogen diffusion behavior, we first introduce microplastic strain by applying preloading at 1000 megapascal. The introduced plastic strain was 0.0%. Then hydrogen permeation tests were conducted with various stress conditions, 1000 megapascal or less, to keep the microplastic strain constant. The left graph shows the transient of the hydrogen permeation current. The greater the loading stress, the larger the steady-state hydrogen permeation current. The right graph shows the enlarged graph in the initial half hour. The greater the loading stress, the faster the hydrogen permeation increase. Based on the result of hydrogen permeation current, we also calculated the hydrogen diffusivity and relationship between hydrogen diffusivity and elasticity are shown here. Hydrogen diffusivity increased with increasing stress. It means that elasticity affected hydrogen diffusion behavior. Finally, I would like to compare the previous result with our result. Previously, the effect of stress were investigated without consideration of microplasticity. It means that it is investigated with various microplasticity. In that case, elasticity increased hydrogen diffusivity, whereas microplasticity decreased hydrogen diffusivity, resulting that elasticity seems to have no effect on hydrogen diffusivity like this. On the other hand, in this study, we investigated the study stress effect with same microplasticity. And we clearly observed that